Hi everyone. Today I'm going to present how to learn dual mean field games on Graph. Before introducing our proposed game, I would like to first give a brief overview of mean field game system. Mean field game models decision-making of a large number of agents. There are many real-world scenarios depicting this game, such as the flocking behavior of birds and the crowding of pedestrians. A mean field game usually consists of the decision-making of a representative agent and the population dynamics, which capture the evolution of the agent maps triggered by the generic agent. In this work, we focus on a more complicated mean field game. We call it dual mean field games on graphs, which models decision-making on both nodes and edges in the graph. This game is motivated by the following examples. Consider a scenario where a large number of autonomous vehicles navigate a road network. Each vehicle will make the route decisions at the node. Here, we use beta to denote the probability of the agent selecting edge 1, 2 at time t. The vehicle also needs to make the speed choice when it enters an edge. Here we use U denotes the velocity control of a vehicle at time t at the location along the edge 1, 2. The goal of each vehicle is to minimize its own total travel cost from origin to destination. Another direct application of dual mean field game is ride sourcing plan 4, where each driver has to pick up and deliver passengers in the city. At each city zone, drivers are matched to passengers. M denotes the probability of a driver matched to the passenger at time t by the location x. And it can also be interpreted as a probability of the driver matched, interpreted as the successful matching rate. After picking up the passengers, the driver has to select which is the next zone to go. Here, beta denotes the probability of going to the other zone at time t. The goal is to maximize the total revenue for picking up and delivering passengers. We now formally introduce the mathematical formulation of dual mean field games. To make it consistent, we use the autonomous navigation scenarios to denote the problem statement. At each node, the vehicle has to make the route choice to minimize the cost. The pi it denotes the route travel cost from node I to destination when the vehicle starts at the node. The beta is the probability of selecting the edge ij, and Vij is the travel cost to the destination when the vehicle selecting edge ij. Vij consists of two parts. The first part is the link travel cost. The link cost is determined by the population density rho and the generic agent decision. It usually consists of the running cost, congestion cost, and etc. The second part is the terminal cost, when the vehicle exits the edge ij at the node j, which is determined by the travel cost from node j to destination. To sum up, the generic agent in the mean field game selects the route choice at the nodes and speed choice along the edge in order to minimize the total travel cost. It is challenging to solve this mean field game. We introduce existing methods to solve the mean field game system. One way is to formulate this game as a variational inequality. This method only works for some specific cost functional forms and a small-sized system. The other way is a fixed point method, which iteratively solves mean field games forward and backward. This method is computationally inefficient when the size of graphs or networks is large. In recent years, there are many papers utilizing machine learning methods to solve min-field games, which inspires to develop a reinforcement learning framework for min-field game. We now first demonstrate how to formulate the dual min-field game as a Markov decision process. We recall the min-field game system introduced before, which consists of the population state role and the decision-making, including route and speed choice, denoted by beta and u. The dual min-field game is equivalent to the following MDP. The state in the MDP is a population density role over the space domain instead of the location of each individual agent. When the generic agent selects the speed choice and route choice over the entire space, according to the policy pi, it triggers the transition of the population state. The transition matrix is denoted by P, which determined by the decision-making U and beta. The population density over the space domain is then updated. The process keeps going until all agents arrive their destinations. We call this Markov decision process as a population MDP. The detailed proof regarding recasting this dual min-field game as a population MDP can be found in our full paper. We briefly present two nice properties regarding this MDP. So the property 1 shows the decomposition of the transition matrix P into two submatrices. Here U is the matrix determined by the vehicle velocity control on the edge, and B is a matrix determined by the routing choice beta on the nodes. These two matrices indicate the movement of the population on the graph. The physical meaning of the first term is the population who moves to a new position in the graph at the next time step. The second term indicates the population who gets stuck in the previous position. Another property is that the dual min-field games are essentially two interacting min-field games. It means this game can be decomposed into two subgames. One is velocity control, and the other one is the routing game. Each subgame is also a min-field game. This property could be useful when modeling hybrid decision-making, like, for example, two or more classes of decisions in the multi-agent system. Readers can refer to the full paper for the detailed proof and the further discussion on these two properties. Based on the population MDP, we develop a reinforcement learning algorithm to solve it. We now demonstrate how our method performed in the numerical examples. The left figure is the network structure of a small-sized network. We visualize the population density along the paths, indicated by the blue dashed arrows, from origin 1 to destination 4. The axis in the 3D figure denotes the time horizon. The y-axis denotes the parts, and the z-axis denotes the population density. Note that at time 0, there are no vehicles in the network. All vehicles start to enter the network at node 1. And there is a decreasing trend of the traffic flow entering age 2-3. This is because some vehicles select the age 2-4. And we also make a comparison of our method with fixed point methods, which shown in the table. These experiments are conducted on networks with different sizes and solution granularities. It is shown that our methods can outperform the fixed methods in a larger sized network. In the future, we will conduct more theoretical analysis for the population MDP framework and apply it to more complicated scenarios. That's all for my presentation. Thank you for listening.